So how do we work out the correlation? And so what we're going to look at is what's called Pearson's correlation coefficient. Now our line of best fit, that measures the correlation, but it's subjective because where I place the line, I'm just looking at points and going, yeah, okay, I think it fits about here. But we would like things to be precise and exact. So Pearson's correlation coefficient, which is symbolised R if we're just dealing with a sample of data, or rho, so that's the Greek letter rho for population. So we've got every possible piece of data, is used to get a precise measure of the correlation between two random variables. So if we have two random variables, x and y, then the correlation between x and y will be the covariance of x and y over the deviation of x times the deviation of y. So variance, remember, we can work out variance, and that's the expected value of x minus the average squared. Covariance, that is the expected value of x minus the average times y minus the y average. Now we can play around with that, and it turns out we get the average of xy minus the average of x times the average of y, and again it's divided by the deviation of those multiplied together. And as I said before, correlation will always end up between -1 and 1. -1 would be a perfect correlation in that as one goes up, the other goes down, but it would be perfect. +1 would also be perfect, but they're both going in the same direction. Strong correlation, we say between 0.6 and 1. Moderate correlation, 0.4 to 0.6. Weak correlation, 0.1 to 0.4. Virtually no correlation at all, 0 to 0.1. And if it's 0, then there is no correlation whatsoever. So I'm saying, if the correlation is positive, then we know as one increases, the other increases. If it's negative, as one increases, the other decreases. So let's work one out. So here's our example. We've got the birth weight and the weight of those same people at age 21. And I'm just going to use 8 pieces of data to, well, basically make the calculations easier. So here's our data. We want to construct, first of all, a scatter plot of that data. And from the plot, how would I describe that association? Just by looking at it. So here's my scatter plot. It does look to be linear, and it appears to be a strong correlation. It's definitely positive, but let's see. We can actually calculate the correlation for that data. So X is going to represent the birth weight, Y will be the weight at 21. So here's my data for X and Y. We'll need to sum these up to do our calculations. So the sum of X, 22.7, sum of Y, for the 438.6. I'll also need to multiply those two together. There's all of those multiplied together and the sum of that row. I will need X squared and I will need Y squared as well, and add each of those up. All right, now I should be able to do our calculations. So first of all, the average of X will be 22.7, so the sum of the X column divided by 8, so 2.8375. Average of Y, that turns out to be 54.825. Now the XY column, if we average that one out, we get 157.025. So the next thing to do is to work out the deviation. So we work out the variance first. So the variance squared would be the average of the X squared row, 66.59 divided by 8, minus the average squared. And notice I've used the exact value there of 22.7 over 8 rather than our approximation. So we end up with 0.5219. Let's do the same for the Y values. So again, it's the average of the Y squared row minus the average of Y squared. Okay, now I can work out the correlation. So average of X times Y, that was 157.025, minus the average of X times the average of Y, divided by the deviations multiplied together, we end up with a correlation of 0.7862. Yes, we said that was a strong correlation. So what we guessed by I was indeed correct. There's a strong, positive, linear correlation. Now, the least squares regression line. This is where we get an exact line of best fit. Not just guessing, but we come up with an actual line based on the correlation. So the process of fitting our straight line to the bivariate data, that's known as linear regression. Now, the method assumes that they're going to be linearly related, and it works good when there are no outliers. What it does, it minimizes the vertical distances. So some points will be above our line, some points will be below our line. But the sum of all the squares of the distances, we want that to be as small as possible. And we also want to make sure it passes through the point of the two averages. So whatever the average of x is and whatever the average of y is, plot that point. We want it to go through that point. So therefore, we come up with an equation. The slope will be the covariance of xy divided by the variance of x. So in other words, it'll be the average of xy minus the average of x times the average of y. That was our covariance of xy. But we'll divide it by the variance of x. Another way of saying that, if we've already worked out the correlation, we say, well, it's the correlation times the deviation of y divided by the deviation of x. Now, why x and not y? Well, because x was what we had on the horizontal axis. Now the y-intercept, we know it'll be the average of y minus the slope times the average of x. Basically, I'm just playing around with the y equals mx plus b formula. So again, draw a line of best fit and find its equation. So I've made that my line of best fit by I. How can I find its equation? Well, I want to locate 2 points that are definitely on that. Now, looking at mine, 250 is definitely on that line. The other point I'm going for is 0.27540. In other words, where it intersects the horizontal axis there. Work out the slope the usual way and put it into the point slope formula. And I end up with this expression. Y equals 5.7971x plus 38.4058. Now that was the one I did by I. Let's now calculate the least squares regression line. Okay, the slope will be the correlation times the deviation of y divided by the deviation of x. Turns out to be 5.36. Calculate out the y-intercept using my formula before, 39.616. So I've got that the line is 5.36 plus 39.62. So how's my line of best fit compared to that? Well, so let's graph them on the same one. There's my line of best fit. If I draw in the one that we just worked out, so again, I'll plot some points that I know are on this line and draw a line through it. We can see the difference there between my line of best fit and the actual regression line. All right, so exercise 15E, going to do A, B, D, F, G, H, I, J in all of the questions, but use the theory formula to do these. I think you'll find it easier than the ones that they're getting you to do in the textbook.